Okay. Looking good. Okay. So hello everyone and welcome back to our simulation of Conway's Game of Life in OpenGL. Today we are actually going to be rendering our stuff to the screen, which is going to be very exciting. And we're going to be going through a lot of tricks that are particularly fun and cool. And we'll see a lot of optimizations, a lot of shortcuts that we can use. And I like this project because we're actually going to be able to see some of the true power of these shaders and how unique we can make them and how we can customize them to this application to optimize our program, which is going to be very cool to look at. So I will just go ahead and switch over to my desk, or let me actually go into OneNote first and then I'll switch over. And then just okay. So we should be, yep, alright, we're looking here. So the main goal of today is figuring out exactly how to get our grid of Conway, which is this, which is represented as a bunch of zeros and ones based on if the cell is alive or not, and we need to render this onto our screen with the window using OpenGL, where these cells map exactly here. So we'll have these grid lines here that are not actually shown, but you guys get the gist. So we need to figure out how to do this, and the way that we the logical way is, instead of copying data over, instead of making an integer array or a float array containing all the positions of each cell, why not just use the data that we've already processed and operated on in each generation? So every Conway structure, if I get this out, every Conway structure has the character, the string representing the board, and this is that string of ones and zeros there. So what if we were just to pass this whole string into the shader itself? So in our previous OpenGL project, we had this whole we've only seen really passing floats and not even integers. Well, I don't think we've actually passed integers into our shaders through the uniform, but for Vertex data through the VBOs, we've only been passing floats, either through floats themselves or 2D vectors representing a 2D position on the screen or a 3D position in the world, stuff like that. But we've never actually looked at passing in just a string of zeros and ones, or just a string in general. And it turns out that you can do this, and we are going to do that today. And it's going to be as simple as just taking this string and passing it into the vertex and into the shader. And then what we do is we will pass this string, blah blah blah, whatever, and for each character will represent its own vertex. So instead of creating an array, what we could do is we could take this string, and on the CPU, every loop, every iteration, we create a vertex array of floats, or just an array of floats representing the position of each active cell. And better yet, we could even do the corners of each of the cells. So if this represented these 3 cells as active, then we would need to pass in we need to pass in a lot of vertices, and that would not be very fun. And it would also be very computationally expensive. But if we just pass this in, instead of just skipping that, and we pass this into our shader, so we'll say this is our vertex shader, and this is our fragment shader, and then this outputs to the screen. Also, I'll just actually just copy this over. And then this will shade in those 3 cells specifically. And the way to do that is just by passing it in through the vertex buffer object, the VBO. So every time we create a new generation, every time we simulate Conway, we will just update the string using GL buffer subdata. And we've seen updating data using the VBO, and we've seen how to do that efficiently. But when the vertex shader takes in the VBO, it needs to figure out, okay, if I'm taking in one character at a time, so it will take in, say, a 0. It isn't given too much, and we'll see what it is given because there are global variables that OpenGL passes into its shaders, such as an ID. And much like the way in Conway where we would use an integer as just our counter, as the integer as the index in the string, that's pretty much what this vertex ID will be. So somehow we need to figure out how to map that integer, which is kind of like this here, the index in the string, and we need to map that to a position. And the way we're going to do that is simply by doing the opposite of, where is it? This right here. Oh wait. Yeah, something of this sort. So we're going to be doing operations to determine the cell, the coordinates of a cell given its index in the 1D string. So if we're given a value 0, then the vertex shader will figure out, all right, what index is it, and then from here we need to figure out how to emit 4 vertices, because we want to, for each cell, we want to actually render a square, render a cell. So we need 4 vertices, and I'll just 4 vertices. And the way to do that is using a geometry shader, because the vertex shader only takes in a vertex, and it will pass along the data to the fragment shader. But the geometry shader is where you can really take a hold of the customization of your rendering process, because we can pass in just that single vertex, or the single vertex position, and pass in, and then from the geometry shader, which is this intermediary step here, we can output 4 vertices, and these 4 vertices will go into the fragment shader as a square, so it's technically 6, but we'll see how we can just do 4, and it'd be nice. So we'll go ahead and into Visual Studio, and we'll see exactly how this is going to work. So we'll actually go ahead and create our shaders first, because I think that's the best way to implement this, or to teach it. So I just need to find where I'm going. So I'm going to say, so I'm just creating 3 new files in the command line. And they're each going to be one for the fragment shader, one for the vertex shader, and one for the geometry shader. So we'll start with the vertex shader, and that is going to be the first step in the path. So first line of all of our shaders needs to be hashtag version 330 core, and then we're gonna take in our layout variable. So it'll be layout, and then this will be the only attribute that we actually pass in for each vertex. So we'll just say location is equal to 0, and then this is taking it in. And to take in a uniform variable, it has to be a 4-byte value. So we're just going to take it in as an integer value. But what will happen is we will only consider the bottom 8 bits, the least significant byte, because that's just how the characters will be passed in through the integer structure, or through the integer memory. So it's only occupying the least significant byte. And then we'll go into our main method here. And then here, what we're going to do is we'll start by calculating our coordinates, or the grid coordinates. And as I said before, we need to use an external global variable, the index. So we're using index, and there is a global variable, and it's called GL_vertex ID. And this is a really helpful variable. It essentially just passes it. This takes the value of the current index of the value. So when we use GL draw arrays, what will happen is when you say 0 to 4, ID will take every value from 0 to 3 inclusive, 0 to 4 exclusive, based on just the index of the current vertex. And if you use an element buffer object, then it would take those indices that you pass in. So we're going to use this global variable here. So we'll start by calculating the row, so float row, and we want to make it a float value because that's what we need to pass in as the coordinates. We're not going to be using any orthographic projections or anything. It's simply just going to be, we'll just be using the normalized coordinates. It'll make it a little simpler. So the row will be the float value of GL vertex ID divided by width, and then float column is equal to the float value of GL vertex ID modulo width. So let me diagram out what this means. So back in OneNote here, if we have a 5 by 6 grid, okay, this isn't working, so I need to type this out. So we have a 5 by 6 grid, and I'll just insert a table here, just like that. So this is our 5 by 6 grid here, and this is equivalent to, this is equal to 30 cells. And each one of these cells has their own index. And if we're storing them row-wise, it goes 0, 1, 2, 3, 4, 5, 6, 7, and you keep counting row by row until you get to 29. So if these are the indices of the string, these will be the indices that are stored in GL vertex ID once we process each string. So what we're going to do here is we want to figure out a way to convert this value 7. That 7 needs to go to a coordinate 1, 1. Where, I'll use a better example. 8 needs to go to coordinate row 1 and column 2. So we need to figure out that given the width, so width is equal to 6, height is equal to 5, we need to convert 8 to 1, 2. And it turns out that the way you do this is just 1 is equal to 8, integer division by 5, or by the width, and then 2 is equal to 8 modulo the width. So 8 modulo 6. That gets the column, and then integer division gets you the row. So the integer division is essentially how many complete rows there are before this, and then the modulo is how many cells do I have to get up to the current column after like in the incomplete row. So that's why we're doing the division, which is implicitly integer division, and then the modulo, and we convert these to a float here. And then what we're going to do is we will output a GL position. So this has to be a 40 vector, and we're going to output the bottom left coordinate of each grid cell or each box. And what we have to do is we need to take account for the OpenGL screen. The normalized OpenGL screen is, oops, that's kind of bad. It has our origin at 0, 0. The bottom left is going to be -1, or I could be wrong about that, but we essentially have to go from our 0, 1 that gets us the float value here. So we essentially just have to convert a map of 0, 1 representing the proportion to -1 to -1 to 1, and the way we can do that is x is equal to or x prime, which is in this one, so x prime is going to be x times 2 minus 1. So we're essentially stretching the interval and then shifting it over to be normalized in -1 to 1. However, what we first need to do is convert this float value. We need to normalize it by the dimensions. So this has to be between 0 and 1. So the way to do that is, since we have a coordinate of the row and the column, we need to just divide it by the dimensions. So we take, so for example, with our example with the index 8 here, so 8 has been now taken to 1, 2 as coordinates, and then we need now to normalize this to 0 to the interval 0, 1. So this is the grid, and then we go to 0, 1, and to do that we just divide by the dimensions. So this becomes 1 over the number of rows, which is 5, and 2 over the number of columns, which is just 6. So this becomes 0.2, 0.33 repeating. So these are the normalized coordinates, or these are the proportion coordinates. So the essentially 0.2 and 0.33 would be over, so this is 0.2, something like that, and then 0.33 is up here. So these are the normalized coordinates. So 0.2, 0.33, and then we now need to convert this to a -1 to 1 using that formula of multiplying by 2 and subtracting 1. So this formula up here. And all we're going to do, so 2 times 0.2 is 0.4, minus 1 is going to be minus 0.6. So we essentially just convert each coordinate, so the 0.2 goes to minus 0.6, and then the 0.3, 2 times that is 0.666, minus 1 is going to be minus 0.33 repeating. So we see now that let's just say this is our -1 there, and then this is the 1, 1. And our OpenGL screen, which needs the -1 to 1 range on each of the axes, we need just to create this little process here of taking the grid cells in the grid cell coordinates to the normalized coordinates, which is just the proportion or the percentage across the screen, and then we need to normalize that to a -1 to 1 range. So what we're going to do is, for the column, we're going to say col divided by width f. So the column is up here. The width f will be a uniform value, so we need to take it in. So uniform float width f and uniform float height f, same way, or just for the same reason. So we're going to multiply this by 2 because our column divided by width f is the proportion. So we multiply this by 2 and then subtract 1. And then same thing for the height. So row divided by height f times 2.0 minus 1.0. And then 0.0 for the z, and then 1.0 for the last coordinate. And that last one is just there for shading values to make sure all of the computations work well. And then I also forgot to have the width here as a uniform value. So this will just be a uniform, and this time it will be an integer because we want to do integer division here. So uniform int width. Perfect. So this GL position here will be the output of that. And then a little bit of a little bit of an optimization here. If we don't want to render the cell, so say the cell is dead, we don't want to render anything there, we just want to keep the screen blank, all we would have to do is, instead of rendering the cell black, we could just discard it or not send any vertices to the fragment shader. But to do that, we would have to pass some sort of flag to the geometry shader, which will actually be which will actually emit vertices, because standardly, or in standard, if you don't have a geometry shader, it will implicitly take a group of 3 vertices making up a triangle, or whatever mode you're using to render. So for a line it'd be 2, for triangles it'd be 3, and it would take that group of vertices and pass them, and the geometry shader would implicitly receive a triplet of vertices for a triangle, and then pass those 3 vertices on to the fragment shader. And what we can do is we can overwrite the geometry shader, which we will be doing for several purposes, but one of them will be to actually just not send any vertices if we don't have an alive cell. So all we're going to do is we will have an output structure to the geometry shader, so an output structure here. So it's going to be out vs underscore out, and we'll name this vs out there, like so. And this is the only way to pass in integers, so we'll say integer valid. This is the only way to pass in variables from the vertex shader to the geometry shader that are not implicitly the GL position, because that will be passed in, that's already passed in automatically. And I mean, I can get the learn OpenGL geometry shader, because it has a good thing here. But essentially this is implicitly what the geometry shader will take in. So it will take in these types of structures, and we can also pass in a different structure with it, which will be passed in as an array, because like I said, the vertex shader or the geometry shader will take in triplets of points if you don't overwrite it. So all we're going to say here is just we'll assign the value of the cell to valid. So vs out.valid is equal to value. So we're going to tell the geometry shader whether or not to emit vertices. And I mean, I guess we could kind of just make a little more, a few more optimizations. We'll say if value is equal to is not equal to 0. So if there is a present value, then we're going to tell the geometry shader to emit vertices. So vs out.valid is equal to 1, so it's a non-zero value, so true. And then we'll compute the GL position only if the value is non-zero, and then otherwise we say vs out.valid is equal to 0. So tell geometry shader not to render. So this is just the structure that we'll use to communicate with a geometry shader, and then implicitly this GL position will be 0, 0, 0, 0 if we don't tell it to do anything, if we don't set anything for it. And we don't really care because we're not rendering, so we don't need to perform these calculations, which will be nice. All right, so one quick recap. We take in the current cell, which is just going to be this single byte from our string as an integer, just because we can't take in a byte. OpenGL will copy the byte to an integer allocated value, but we can't put in byte there. It has to be an integer. Then we take in a few uniform values for dimensions. We are going to be outputting the validity or the state of the cell. And then in the main, we need to calculate the grid coordinates and then output the bottom left coordinates. So I'll just put here once again, we go from grid cell to the 0, 1 by 0, 1. Just that's a 2D, that's just that coordinate system there, and then we need to go from that to the -1 by -1, 1 coordinate space there. Only if the cell is valid. Alright, let's go into our geometry shader now. And it's going to have the same first line, so it'll be hashtag version 330 core. We're going to be taking in from the vertex shader. So we're going to take in layout points in. So this is telling the vertex shader, all right, I want points. I want single values. I want single vertices. I don't want you to send me a triplet of points. You could say layout triangles in, and what it would do is it would send you a triplet of points, but we only want a single point at a time. And then we're going to output a square, which is 4 vertices. And we can output a cool method called triangle strip, which automatically fills in the triangles for us. So layout triangle strip, and then the max vertices is equal to 4, and that's going to be our output there. Triangle strip, once again, will just automatically convert our 4 vertices into triangles, and max vertices is 4 for the square. And then we're going to take in 2 uniform float values, uniform float cell width and uniform float cell height. And these will just be the normalized normalized widths and heights of each cell that we want in our screen. So this will be based on the -1 to 1 scale. And then on the opposite, or on the other hand of taking or outputting the VS out, we need to take this in now. So we're going to say in, and we're going to call it VS out for the same capitalized name because it's the same structure. It's still the vertex structure output, and we're going to take it in as a GS input, geometry shader input, and it's going to be an array because we're going to be taking it in for each vertex. And it's going to be integer valid. That's the only member there. And then we'll just have our main method. And we're going to do our check right here. If GS in at 0, because this is going to be, we're only taking in 1 point, if GS in at 0.valid does not equal 0. So if it's a non-zero value, if it's true. And we only want to render the cell if it's alive. And we can create a helper method to kind of simplify this. We'll just call it void build cell, and we're going to take in a 40 vector pose, and we'll call this method in the if statement. So build cell, passing in GL in. So implicitly the geometry shader takes in a GL in, which contains these values here: the position, the point size, and clip distance. So GL in at 0, because once again it's only a single point, dot GL position. Right, and then in build cell we're going to do our 4 coordinates, or our 4 corners. So the way it's going to work is we're going to set GL position and then emit a vertex. So GL position is equal to pose, and that's the first coordinate, and then we call emit vertex. And what this will do is it will send it to the fragment shader. Then GL position is equal to pose plus, and now we're going to go 1 width down. So we'll go down the x-axis. So pose plus the 40 vector cell width on the x-coordinate, and then 0.0 for the rest of them. And then we're going to emit the vertex. And emit vertex, we'll send this to the fragment shader, but GL position is implicitly, it will be a global variable. So by setting the global variable, the fragment shader now has access to it. And then GL position is equal to pose now plus the height. So cell height 0.0, 0.0, and 0.0. And then we're going to emit our vertex again. And then finally will be the upper right corner is equal to pose plus vec4. And now we need to add the width and the height. So cell width in the x, cell height 0.0 and 0.0. I made a mistake here. This vec4, the second one, should be 0.0 on the x, and then the cell height should be on the y. And then after the fourth one, make sure to emit vertex. And then after this, we end the primitive, telling OpenGL, all right, we're done. We sent you our triangle strip with 4 vertices. Now make us a shape. And it will render it in the screen according to the fragment shader, which will just be a simple one-liner here. We just do hashtag version 330 core, and then we output a vec4 color. And in the main method void main, we simply just say color is equal to vec4 1.0 for white. So that's the entire shader. Start in the vertex shader, taking in our characters or the values for each cell in an integer. Calculate the grid coordinates, and if the cell is valid, honestly, we can even simplify this a little further. We can optimize this a little further. If the value is 0, then we want to do stuff. So we can just put all the calculations in that if statement. Otherwise, we just set the valid to 0. So once again, we're calculating grid coordinates, which is just, for 8, it would be the row and column, and then we move this to a range of proportions, so just 0 to 1, and then we normalize that to -1 to 1 for OpenGL. And that's it. That's the shaders. And then, that's the vertex shader. Pass that in through GL position. And then in the geometry shader, if we have a valid cell, then we're going to emit the 4 vertices, the 4 corners of the square. We're going to emit each vertex, then add the primitive. And then in the fragment shader, we just set it to white. And that's good and good. And yeah. Alright. Now that we are done with that, we can go into main.cpp. And we'll start with our stuff. So we'll go to the top here. And we need to change a few of these parameters. So width and height did hold our screen width and screen height. However, we now want to be able to calculate that to fit our window to the Conway grid. So we're going to change the width and height to whatever the Conway grid is. So let me actually just minimize this stuff here because we won't need it. Well, we're going to use the shader methods, but they're not of concern to us right now. So this width will become what we have over here, the define x and y. So x is the height and y is the width. I'm still trying to figure out a better way or a more proper way to do the width and height here, because I don't want to do the defines, but I have to for the array. It's not allowing me to do a constant unsigned integer, but I will try. Alright, so that's the parameters there for the width and height, and then we also want to specify a cell dimension. So this will be the size in pixels of each cell. So it'll be a float value. Cell dim is equal to, should this be, I'm not sure if I want this to be a width or an integer or a float. Let me check here. Oh no, this can be an integer. So it's going to be an unsigned integer. Cell dimension is equal to 20. So we'll just have 20 pixels for each cell. And then we have regeneration frequency over here, which is all good in what we had before. And we kind of went through the reasoning behind this, but I will reiterate it once we get to the main loop. So before we start rendering, we need to actually calculate our new parameters. So using the new width and height, we need to reset the set up the table accordingly. So instead of having width and height as just the pixel widths and heights, we need to pass in width as the width becomes width times cell dimension, and height becomes height times cell dimension. So we want the window to be perfectly fitted to our grid, so that every cell, so that we can fit the amount of cells on the window. So we have number of cells in the width and number of cells in the height, and we just multiply it by how many pixels per cell, and that gives us the window size in pixels, which is exactly what we want. All right. Next, we're actually going to worry about our shaders. So once we've set the viewport, we can set up shaders. So we'll start by generating our shader program, GLUint shader program, and this will just be the line that we, the method that we called. Oh, that's a fire truck. Sorry about that. Just calling the gen shader program, and we'll pass in the window, or sorry, the paths are going to be main.vs, main.fs, and main.gs. Thank you for the kind words, Allop memes. I like that name. So yeah, this is just the gen shader program, the function that we had last time, that will take these three shader paths that are relative to the project directory, and will compile our shader. But now what we need to do is actually set some of these uniform variables, because we have these uniforms here that need to be set before we start rendering on our CPU, because it doesn't know what the width is until we actually set it. So we need to set the width as a float, and the height as a float, and then in the geometry shader we need to set the cell width and cell height. So all this is going to be is we need to use the program first. So set width, or set dimensions. So GLUse program, passing in the shader program. And then we're going to first set the, I forget which ones we have. We have the width, and then the width and height as a float. So GL uniform, that's just setting a uniform variable, and then we need to tell it what type. So 1 for one variable, and I is going to be an integer. And to get the location, we need to say GL get uniform location, passing in the shader program, and the name will just be, I forget which, width. So the name is just a constant character pointer, and then we set the value as an integer, which is just c.x. And then GL uniform 1i again, or the width should be c.y, sorry. And then we need to set the float values. So this will just be 1f now, sorry. For a float, GL gets uniform location shader program, and the name will be width f, and then the value will be a float conversion of c.y, and then something similar for the height float. So GL uniform 1f, GL get uniform location shader program. No, I'm not from California. I will not disclose my location, but no, I am not from California. It's way too warm over there. And then the height will just be the float conversion of c.x. And then the other two uniform variables that we need are the cell width and cell height for the geometry shader, which are going to be one float or single float values as well. So GL uniform 1F, GL get uniform location, and we pass in the same shader program because these three shaders will be compiled and linked in the same program. So shader program, same ID, and the value will be cell width, and this value is going to be, so cell width needs to be the proportion that 20 pixels takes over the entire screen. So let's go back here and we'll take another rectangle. And let's say we have our 6 columns and 5 rows. We could make this a class, but we're using one shader here. It's really in the engine, in the big OpenGL tutorial, we have this class for that, but this is just a simple side project. I'm not looking to do anything fancy. I'm just literally keeping all the code in this one file here, at least for the OpenGL stuff. So we have 5 by 6. I'll just draw some lines, kinda. So if we want to get the proportion that one of these cells will take, so if we know that this is -1 to 1 and the height is going to be -1 to 1, I believe, and we want to figure out what are the relative dimensions of this cell in the normalized coordinates. Well, it's going to be this initial position, the final position minus the initial position in both coordinates. But to make this the same for each of them, it's just, you can kind of just think about, all right, well, if we know that we have 6 cells and they're all the same dimension, what's the whole range here? So this whole range here is 2. So we have 2 units to distribute to 6 cells across the width. So all we just need to do is 2.0 divided by 6, and that gives us the relative width. And I think we saw that, or we saw something similar to that, but 2.0 over 6 will just be the relative width of each cell. So it'll be 2.0 float divided by the float value of width. And then similarly for the cell height, so GL get uniform location, shader program, and cell height is now the name. It'll be 2.0 float divided by the float value of the height. Now that I'm thinking about it, we could do a little bit of a tricky thing here. What we could do is just, instead of dividing here and normalizing, what we could just do is, for the column position, we could say column times cell width minus 1.0. And that should work, because 2 divided by width is just cell width, as we saw right here. And 2 divided by height, which is this right here, is just that cell height right there. So we can actually just pass in row times cell height minus 1.0, and we need to subtract 1.0 again, because multiplying up by 2 brings it to a 0 to 2, and then we just need to shift it by 1 back. So what we will do now is just pass in the same uniform variables to the vertex shader. So we can replace the other floats with the cell width and cell height, which reduces the need for two extra uniform variables. So we can delete those, the width f and height f. Would I recommend making a large project game engine in Java? I mean, Java is fine. You could do it. There's the LWJGL that you can use for OpenGL. I like C++ just because you can manage memory better, but Java works just as fine. They made Minecraft in Java, so it's also Java's also a little easier to program in. So if you're more of a beginner, you can definitely try that. But I like C++ better, just because it gives you more control. But the process I think is very similar, because OpenGL is still the same, and OpenGL is the same regardless of what language you're programming in. It's just how you communicate with OpenGL is what differs from platform to platform and language to language and library to library. Alright, so these are the three shader uniform variables that we need to set, and now we need to actually set up the pathway to send our string to the vertex shader using our vertex buffer object and the vertex array object. So that's the shaders, and then set up VAO/VBO. So what OpenGL does is it creates a vertex array object for every object that for every model that you're going to draw. So it's considered a GLU unsigned integer because it's an ID. We're just storing an ID on the CPU. So it's a VAO, and what we do is we generate it, calling glgen vertex arrays, passing in 1 because it's just one of them, and then a reference to VAO, and then glbind vertex array, passing in just VAO for the integer. And the VAO will have several members with it. It will have vertex buffer objects that actually hold the vertex data. But what's cool with OpenGL is you can have multiple vertex buffer objects for each VAO. And due to this, you can then pass in multiple forms of data for each object or for each model that you want to draw. And you can tell OpenGL, all right, I want to draw this model, and if I just tell you which VAO, I know you'll be able to take care of it. So we just need to bind the VAO every time we want to draw this model, and it will know exactly what data to look at. Yes, that is true. Yeah, serialization is a lot simpler in Java. That is true, yeah. And platform independence, yes, that is also true. C++ works on all the platforms, but there are a lot of different things. Like GLFW is platform, well, it's cross-platform, but there are calls that are going to be platform specific. Not a problem. The axial. All right, so that's the VAO. And now we're going to do the VBO. So it's going to be another integer, GLU into VBO, and glgen buffers, 1, and then a reference to VBO. All right, so then we're going to set our data. Let's put this right underneath it. So here, we're going to need to bind the buffer. So I'll just bind it up here, actually, glbind buffer. And the target will be the GL array buffer. So the current array buffer that we want to write to is just going to be VBO. And then setting the data, as I said before, we're simply going to be able to just pass the string in. If we've already processed all the data for Conway, I don't want to double process it, put it into a float array. I don't want to do any of that. Serialization is not that I'm aware of, not the same way that it is in Java, but you can definitely write something to do that. where was I? Yeah. For setting the data, we're not going to pass in a float array. So we're simply just going to throw in the string containing the Conway grid. So GL buffer data, that's a way to set data. The target will be GL array buffer. The size is going to be, well, what's the size of our string? It's going to be the number of cells times 1, which is the size of a character. So c.x times c.y, and we can just leave it like that. And then the data will be c.board, because that's the pointer to the data. And then we want to do GL dynamic draw. And the reason why it's going to be dynamic draw is because we are going to be updating this this data pretty often. So I'll just using operator and then casting to an 8. What is it looking for? Yeah, so we're going to be changing this data every time we actually generate a new or simulate another generation. So that's why we want to do dynamic draw. So it's because then OpenGL will store it in a more accessible location. So we set the data, and now we need to tell OpenGL how to actually read it. So this is going to be done through attribute pointers. So set attribute pointers. So GL enable vertex attribute array and 0, and make sure that this 0 here, that index, has to match with our vertex shader location is equal to 0. So this is going to be our vertex attribute array. Okay, hold on. I've always had a problem with my microphone. I'll just turn the gain up a tad. Maybe that should be a little better. I don't want to blast it because then it's going to blow things up, but I hope that's a little better. Yeah. Okay. So yeah, location is equal to 0. That is the index of the attribute that we're looking at right now. Those must match. And then to tell it how to write it, we're going to say GL vertex attrib, and then we're going to do I pointer. So I is going to be for integer, and pointer is going to be, or just I for integer, and then that's the method to set the method, or the way to read the memory. So we set 0 for the index, same index. The size will be the number of bytes, or the number of elements per unit. All right, awesome. So the size will be 1, since we're sending in 1 byte per vertex. So the number of elements per vertex here. The type will be a GL byte, because we're just sending in 1 byte. The stride will be the size of a character, which will just be 1, and then the pointer will be 0, or the offset. So in other words, we want to tell OpenGL to read this at index attribute index 0. We're going to say 1 GL byte per vertex, and then we're going to stride the size of a character to get to the next index. Just like that. So 1 GL byte per vertex, and stride 1 byte, or the size of a character, to get to the next vertex. And that's all it is. And that's our VBO in there. And then the only thing to do now is render. I mean, before we do that, I'm going to take care of some cleanup first. So after the main loop, we're going to clear our buffers and arrays. So GL bind buffer, GL array buffer, and 0, just to clear that, and then GL bind vertex array 0, just so nothing is bound when we delete. So delete the buffers and arrays, GL delete buffers 1 and a reference to VBO, and then GL delete vertex arrays, passing in 1 and a reference to VAO, and then we delete the shaders. So GL delete program, shader program. So the cool thing about OpenGL is that the way we call the generation, GL generate buffers, GL generate vertex arrays, GL generate program, it's the exact opposite to delete it. So we generate a buffer, then we delete a buffer. Generate a vertex array, then delete a vertex array. And then I put the rest of the termination in a separate method here, up top. That should be on the new GitHub commit, but nothing wild. All right. So now let's actually go into our main loop. So we're going to create a helper method to render the screen, because what I want to do is render the screen before we go into the loop. So I want to render the initial configuration. And then also, once we have a new generation, then render the updated state. So we'll do this using a single function here that takes in a few inputs. So I'm going to put it above the main loop, or the main method, and that'll be up here. Void render screen. We're going to pass in a glfw window pointer window. Then a GL uint shader program, the Conway structure, GL uint VAO, and GL uint VBO. So these are all the parameters that we're going to need to actually render. So the process of rendering is pretty simple. We clear the screen first, then we're going to render our objects. Here we only need one, and then we're going to swap the buffers. So OpenGL will render to a buffer, and then OpenGL essentially stores 2 buffers at a time. The one that is currently on the screen is one of them, and then it writes to the second one every iteration. And then once it's ready, we will swap the 2 buffers and write to the one that was on the screen in the next loop. And so on and so forth, and they keep swapping. So we'll start by clearing the screen. So clear screen calls GL clear color on 0.0, and this will just make it black, and then 1.0 float, and then GL clear GL color buffer bits bitwise ORed with GL depth buffer bit. So this is just our we're just clearing all the stuff from the previous rendering to the buffer that is not currently present. So this is the buffer that is behind the scenes now. And then we're going to render our object, but as I said before, we want to update this state. So we first have to update the data before rendering. So GL bind vertex array VAO, GL bind buffer, GL array buffer for the target, and then the buffer itself will just be VBO. And then just update data, we're going to call GL buffer subdata. GL buffer subdata, which has quicker access time than GL buffer data when we're not initially setting it. So we need to call GL buffer data to allocate the memory, but GL buffer subdata will just replace memory. So we call GL array buffer for the target. The offset will be 0 since we're replacing all the memory. The size will also be the same, so c.x times c.y, and then the data will be c.board. So we're just passing in the string, the updated string, into the shaders. And then to render the object, we're going to be considering the grid as one model. So that's why I only have one object here, and why I don't have a plural there. But we're just going to be rendering our grid as just one object in and of itself, and each of the points will be its own vertex. So what we'll say here is GL use program, pass in shader program to tell OpenGL, all right, we want to use this program. Quite similarly to how we called use program when we were setting the dimensions to make sure OpenGL is targeted properly. And then to render it, we're simply just going to say GL draw arrays. The mode will be GL points. And this mode is really where a lot of the magic happens, because we're just telling it, all right, funnel in one point at a time to the vertex shader. And that's what we want for each vertex. We don't want to funnel in 3 points to make a triangle. We just want the one, and that's it. So GL draw arrays, GL points. The first one will be 0, and then the last one will be, or the count will be c.x times c.y. So we want to offset 0, so start drawing from index 0, and then draw c.x times c.y, so the number of cells. We could create a variable for this, but I'm just going to keep it like that for explicit sake. And then we swap the buffers. Do this simply by calling glfw swap buffers, pass in the window. So then once again, this will swap the buffer that is currently on the screen, that is currently being displayed, with the buffer that has been rendered to using GL draw arrays. All right. Now, what we can do is we want to render our initial configuration, which was before the loop. So render screen, passing in the window. The shader program is shader program. Conway is going to be C, and then the VAO and VBO. And then we can do the same exact call in our loop. So every time the timer reaches the generation frequency, then we want to re-render the screen or swap the buffers. And notice how in the other OpenGL engine that we wrote, we were rendering every iteration just because our environment was dynamic and it was changing every frame. But this is only changing every time we swap the buffer or every time we simulate a new generation. We don't need to go through these expensive operations of rendering it every time if we're just going to be rendering the same stuff. We don't need to swap buffers until it's absolutely necessary. I have looked into the Journster stuff, and I'm thinking of doing something of that sort in OpenGL. I'm not sure yet. But yeah, so what we'll see now is we will do our new generation. It'll print it out to the console, and it will simultaneously render it to the screen. All right, so let's go ahead and run, and this is going to be very cool. And shit. Never mind. Okay, so it was doing that properly, but there was something about... It wasn't rendering anything. Let me... Nope. Let me see this here. The window is being sized properly, I know that. Okay, it's calling update every time, but it is not getting the stuff. So let's go look at our stuff. So we clear the color, clear color buffer bit, blah, 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 blah. Bind VAO, bind VBO, buffer subdata on the Conway. Use the shader, and then drop points from 0 to c dot x times c dot y, and then swap our buffers. Alright, so it's updating properly because we're getting the outputs in the console. However, Windows popping up properly. Just this is not working. Generate our shader. Use the program, shader program. Uniform 1 eye and then 2 floats, which is width and then c dot y, then cell width and cell height. Our VAO, the vertex array, bind the vertex array, bind the VBO, generate and bind the VBO. Then we're going to set it c.board as the initial data. Dynamic draw. Enable this. Attrib I pointer 0, 1 GL byte size of a character and 0. The CP, this code looks right. Might be the shaders then? Let me just try setting vs out.valid to 1 and see if that's the problem. Alright, there is not a single point on this, so we're not even getting a 0, 0. Which is not right. Let me just try doing a random position. Because I want to see at least a point. I'm not getting it. Okay. Geometry shader possibly. Let me just try doing a constant here instead of the uniform values. Nope. This is a little annoying that you can't really debug your shaders. Alright, we take in the valid layout points in, layout triangle strip max vertices, 4 out, cell width and cell height. We build the cell using 0. Fragment shader is going to be good either way because I know this is right. Let me actually see if there were any render or if there were compile errors. Ah, here we go. Okay, so it gave us undefined variable GL vertex ID. Oh, you're out of your mind. That is a, no, it is a valid thing. Oh, no, this is embarrassing. I misspelled. I didn't capitalize it properly. Shit. Still not working. What was the? Were there any errors now? There were no compile errors. Okay, I see. Do you see these two things here? Those are 2 dots. I don't know where they're coming from though. Ah. Oh, it's working, but it's small as fuck. You see it's working. It's in the little corner there. That's right. But why is it so small? This isn't okay, it's working, that's all that matters, but it's all the way in the goddamn corner. What's up with this? What is cell width and cell height? Alright. So I'm going to determine what these values are. 0.02. That... is that right? Each cell should take up... this should be 2 over 100. This should be 2 over 30. And that seems right. Is it so small? What's up with the Vertex shader here? This is, but it's working. That's the thing. It's in the little corner there. If I could zoom in, I would. Maybe I don't think I can zoom in, but it's over there. Okay, is this a viewport thing? Maybe. All right, let me just not render. Let me not update, just so I can. Keep the console output up top. Okay. Is it this thing that's not working? Oh, aha, yes. All right, here's the problem. What happened was we were calling frame buffer size callback with the width and height, but we changed the width and height to 130, so it's trying to render to a 100 by 30 in pixels. So what we need to do is pass in these two parameters, the width times the cell dimension and the height times the cell dimension, into the frame buffer size callback to properly set the pixel width and height. Okay, now it stopped. Oh, there it is. Perfect. Okay, that's awesome. Okay, so there is Conway working beautifully. It's going very slowly, but this is our glider gun pattern, and you will see that it's moving opposite to the console because the console is rendering top to bottom. This is rendering bottom to top because it's a standard Cartesian coordinate system, so 0 0 is in the middle, or coordinate wise 0 0 is at the bottom left, so this is cell 0 0 here. And then, but what we do in the console is we render 0 row up top because we're printing top to bottom. This is awesome. Okay, let me go and reprint the table. Yeah, okay. So you should see that it's matching it. It's just a mirror image. I have no clue what that is. Why is that zeros? That is 0 0. I don't know why it's rendering that, because that's not showing up here. Did I play around with something that I should not have? Either way, I'm not really worrying about that right now. I'll figure it out, but I want to speed up the frequency just so we can see the whole thingy. We could honestly go even faster. Let's do 0.25, so 10 times faster. I don't know why there's a thing in the middle there. Yeah, so this is cool. This is but you can see that it's kind of reshaped. I should put a epilepsy disclaimer. So this thing will die. Maybe not. It's still going. And it's in a steady state. Would you look at that? And you can also see that if I resize the window, the cells will be resized as well, because once again we're using normalized coordinates. So this is all relative to our viewport. I can keep doing this. I need to figure out what's up with the middle thing there. Because it's trying to... Did I pause this? Oh no. Sorry. Because it's sending in a 0, 0 somewhere, and I don't like that. So what I'm seeing is the geometry shader is finding is getting a 0, 0 input. Okay. There would be no reason for that to happen. Oh, you know why? Aha. Yes. Because we reset the valid thing here just as a testing thing. This needs to be valid, we need to have it be 0 when we don't want to render, because if it's not rendering, then the geometry shader is just simply getting a 0, 0, 0, 0 as the position. So it's just rendering it in the center of the screen. So now we don't have the thing in the middle, which is awesome and perfect. And yeah, so this is Conway's Game of Life in OpenGL. I will probably do another video at some point, adding a few features, like we can do a pause feature. Might add some user customization here to kind of, if you want to click a cell, add some user input. But for now, this is really, I am psyched about this. This is really cool. So yeah, this has been Conway's Game of Life. This was a lot of fun to do. This was so much fun to do. It was a heartache, and I ran into a lot of bugs along the way, but when it was mainly along passing in the string into the Vertex shader, because I didn't know explicitly how to do that, or how OpenGL actually passed in layout variables that were not floats, like if they weren't 4-byte values to the shader. But once I figured out that you could just tell it, give it a byte, and it would output it into a 4-byte slot, that just pretty much solved everything, which was really cool. But yeah, this is Conway's Game of Life. That's all I have for you guys today. Hope you guys enjoyed and maybe learned something. And I will see you guys when we come and polish this application off a little bit and add some user input. And we can also do some more customization, like adding sliders and stuff like that. And I will try and figure out the array bounds for the Conway structures that we're not left using these stupid macros up here. But yeah, that's all I have for you guys today. Hope you guys enjoyed, and I will see you guys in the next one. Have a good one.